In this video, we take a look at section 4.7, which is a section, sorry, let me zoom in here a little bit, which is a section on something called L'Hopital's rule. It's pronounced L for Lope, and then more like L'Hopital's rule. And it's essentially a method for going back to computing limits. Now that we know a little bit of calculus, we're going to return to the idea of computing limits. Okay, and this video is just going to address the general method, the why of the method. Okay, and just by way of example, notice that to the left of the screen we see some typical problems, some typical limit problems that can be addressed using L'Hopital's rule. Okay, so there's one, and if you take a look at the limit as x goes to 0 of e to the x minus 1 over the sine of x. These two limits have something in common. They are both limits where the function that you're taking the limit of is a quotient of two functions. So we're looking at a quotient of two functions. And what's happening in this case is that we are computing a limit as x approaches a, some number. In this case, a is equal to 2. And in this case, we're taking a limit as x goes to a, where a is equal to 0. Okay? And both of these problems take a look that the function on the left-hand side, the function evaluated at 2 is 0, and the denominator evaluated at 2 is 0. And on this problem on the right-hand side, evaluate the function at 0. You get e to the 0 minus 1, which is 0. And the denominator evaluated at 0 is the sine evaluated at 0, which is also 0. Okay? So what we're seeing here is that we're trying to compute a limit. And our limit, if we plug in the values, we're getting something called 0 over 0. Right? Which is something that we really have to think hard about. And in this video, I just want to say that the method that we're looking at, okay, is that if you have two functions, okay, say maybe f and maybe a function g, here's a function f of x and here's a function g of x, and we're computing the limit as x goes to some number a, right? And I've drawn both of these graphs so that the function evaluated at a along the x-axis gives you 0, and the function g evaluated at a also gives you 0. Okay? So these are the typical examples of what we're looking at, and the trick here for all these L'Hopital rule problems is the calculus trick. And the calculus trick is to replace a function f of x with its linearization, aka its tangent line. So in this problem, what we're going to see is we're going to draw the tangent lines to this function and look at the limit as x goes to a of a function f of x divided by g of x. And instead of doing that limit, we're going to replace the function f of x. Okay, we're going to make a new limit as x goes to a of the linearization, which is the function evaluated at a plus f prime of a times x minus a. Replace the function g of x with its tangent line. Okay. And then use the fact that the function evaluated at a and the function g evaluated at a, that both of those are 0 because the function crosses the x-axis at the value a. In which case our new limit is going to be the limit as x goes to a of f prime at a times x minus a over g prime at a times x minus a. And looking at this limit here, f prime at a and g prime at a, that's the ratio of the slope of f at x is equal to a divided by the slope of the function g at x is equal to a. And those are numbers, so they come out in front of the limit. And then we have the limit as x goes to a of x minus a over x minus a. And because x is close to a, x minus a is never equal to 0 because x is only close. And since they're close but not equal, you can not equal to 0, you can cancel them out and cancel out without losing any information. 1 divided by 1, and that limit is equal to 1. So what we have shown here is that the limit of a function f of x divided by g of x is equal to the derivative of the function at a divided by the derivative of the other function in the denominator at a. Okay? And that is basically, in a nutshell, L'Hopital's rule. Okay? When your function f and g are both 0 at the place where you're computing the limit. Okay? The next step is going to be able to show how to use L'Hopital's rule to actually do these limit problems. Okay? And we can see here that, for example, applying the L'Hopital's rule method, okay, what we have found here is that L'Hopital's rule says that if you want to compute the limit as x goes to 2 of some function f of x divided by g of x, but you get 0 over 0, then we know that the answer is going to be the derivative at 2 divided by the derivative of the other function at 2. So you'll get 1 divided by 2x, but 2x evaluated at 2 is 4, so the limit, this problem here, will be 1/4. Okay? And the other limit will be equal to the derivative of e to the x minus 1 evaluated at x is equal to 0 divided by the derivative of sine of x evaluated at x equal to 0. In which case you will get the derivative of e to the x is e to the x, the derivative of sine is cosine. You need to evaluate both of those at x is equal to 0, which is basically saying f prime at 0 divided by g prime at 0, which will give you e to the 0 over cosine of 0. E to the 0 is 1, cosine of 0 is 1, so you get 1 for that limit. So this limit is equal to 1. Okay, and that's L'Hopital's rule in a nutshell. There are some subtleties, of course, and we will get into those subtleties in the next video. I would say these two L'Hopital's rule problems are on the easy side of the house, and so the next videos will address some more complicated limits.